Okay, so let's think about what we've done in previous lessons. We found the area between the curve and the x-axis. And the way we did that is we took the area of an infinite number of rectangles, added them all up with the integral, and that would give us the area under the curve. The width of each of these rectangles is infinitely thin, infinitely small, and the height, because the area of any rectangle is height times width, the height was given by the function. Okay? And then we found the volume of a figure whose base was defined by a function. And for instance, we did the slices as such. So that looks real good, but you remember from the last lessons. And we had an infinite number of slices, and adding those all up, the volume of all those would give us the volume of this figure. The volume of each one of the slices, the depth, well, the volume of any slice or any figure is the area of the base times its depth or its width. The width of each one of these was infinitely small, so we just had to find the area of each one of these slices, and the integral would add them all up. It would find the volume of all those, add them all together, and that would give this volume of the figure. And the area was defined by the function as well. So now what we're going to be doing today is we're going to be finding the volume of a figure that is formed by the function y equals x, this right here, by the x-axis, by the vertical line x equals 4, and we take this region and we rotate it about the x-axis. So you take this and rotate it around the x-axis. That creates this cone figure as such. And that's what we're going to be finding the volume of. Let me show you this to make it a little bit clearer. Here's our function. Y equals x. X-axis. X equals 4. So we're going to take this region right here and we are going to revolve it around the x-axis. So you can see it ends up being a cone. Okay, you can see the figure that we end up with is a cone. We took that region, revolved it around the x-axis, and we end up with a cone right here. So we're going to find the volume of this. Now, much like what we were doing before, we're going to take these slices, take an infinite amount of slices from A to B, from our starting point to our end point, take the infinite number of slices, add them all up, and that will give us the volume for this figure here, this cone right here. Okay? And you say, well, I already can find the volume of a cone. We learned that geometry. True. But the function that's defining what this figure looks like, it's not always going to be y equals x. It's not always going to end up being a perfect cone. So with all kinds of strange figures, we can find the volume of them by simply taking the volume of these infinite number of slices, add them all up with integration, and that will give us the volume for the figure. Such as this kooky looking thing. Okay? It's bound by this function right here. Okay, so you can find this, the volume of this, by taking the area of an infinite number of slices, add them all up, and that will give us the volume of this figure. This figure is bound by this function right here, f of x. We went from A to B, and rotated it around the x-axis, and it gave us this figure right here. And you can see that each of these cross sections is a circle. Each of these slices is a circle. So what you're going to do is find the area of an infinite number of circles, okay, or the volume, but the width of each one of these, the depth is infinitely small, so we just have to worry about the area of each one of these. And how do we find area of a circle? Pi r squared. What is our radius? Our radius is f of x. It is the radius of each of these circles is defined by the function. So therefore, the area of each one of these cross sections, each one of our slices, is pi times the radius squared, the radius being f of x, so it's pi, the function, squared. And that will give us the volume of this. We'll take the integral. The integral will take the area of an infinite number of slices, or the volume of the infinite number of slices, add them all up, gives the volume of this. And that's how that is going to work. Okay, so like we said before, to find the volume of the figure bound by a function, the x-axis from A to B, revolving it around the x-axis, we're going to find the volume of an infinite number of these cross-sections, which are circular, therefore they are disks. They're called disks. They're going to be infinitely thin, so we just have to worry about the area of each of them. And the area of each of them, the area of any circle, is pi r squared. And so we just have to worry about the radius. And the radius is going to be, the radius of each one of these circles is going to be defined by the function. Remember, our y values are a function of x. Depending on how our x value is, we plug it into the function that tells us how tall it goes up here. That is our radius. So our radius of each one of these circular cross sections, these disks, is our function. So the volume is going to be from A to B, pi r squared, but our radius is simply f of x. So it's our function. So this is how we're going to find the volume for these figures. And this is called the disk method because each one of our cross sections, as we saw, is a disk. Each one of them is going to be a disk. We're going to find the volume of an infinite number of those, add them all up. And there's another method called the washer method, which we'll talk about tomorrow or the next lesson. But this is going to be the disk method. And you use the disk method anytime that the region bound by the function from A to B, if the entire region is touching the x-axis, a little hint, if the entire region is connected to the x-axis, you're going to use the disk method. The washer method is going to be a little bit different, but we'll talk about that next lesson, like I said. Okay, so we're going to sketch this figure and find the volume when the given area is rotated about the x-axis. It's revolved around the x-axis, so make a little sketch. We know y equals x squared. So make it 1, 2, 3, 4, 1, 2, 3, 4. From y equals x squared, which is here, go to 2 to 4. So it looks like this. Everybody remembers parent functions. Okay. X equals 2, which is a vertical line right here. And y equals 0, which is the x-axis. So this is the region that we're going to be rotating about the x-axis. So I'm going to put a circle right here. And I'm going to put a little thing right here showing I'm going around the x-axis. So we're rotating that figure, that region around the x-axis, which is going to create this figure here. So to find the volume of this, we're now going to find an infinite number of disks and add them all up, and that will give us the volume for the figure. So we're going from A to B. We're going to find the area of each of these disks. And what's going to do? The integral is going to add up the volume of each of those because they're all infinitely thin. And that will give us the volume. So we just have to worry about the area. Okay, and remember the area of a disk is pi r squared. So our radius, remember we said, is defined by the function. The radius of each of these is defined by the function. The radius of each of these disks is defined by the function. So we're going to be going from starting point to end point. It was defined from basically the region's bound starting here at 0 and going to 2. So we're going to be going from 0 to 2, pi, and our function, our radius, is x squared. So it's x squared squared. Okay, so this is going to give us the volume of this figure. Now, pi is just a number. It's the most awesome number in the world, of course. Ain't that right, Wesley Boyles? Me and him have that birthday, 3.14, pi day. But anyways, I digress. It's just a number. So with any constant inside of the integral, you can take that out. Make it a little bit easier on yourself. And just worry about it at the end. So I have here, inside the integral, x squared squared, which is x to the 4th. So now I just take the antiderivative of this, which would be pi. The antiderivative of x to the 4th is 1/5 x to the 5th. We're going from 0 to 2. Once again, 1/5 is a constant, so I can move that out, multiply that times pi to get pi over 5. Now I just have x to the 5th from 0 to 2. Makes it a little bit easier on myself. So it's 2 to the 5th minus 0 to the 5th, which is pi over 5 times 32, which is 32 pi over 5 units cubed, because we're finding the volume of a figure. Excuse me. Okay. So let's look at another one. This is defined by the function root x plus 2, the line x equals 0, the vertical line x equals 4, and y equals 0. Okay, so let's make a little graph of that. We know this. Okay, this is simply the parent function root x, vertically translated 2 units. So now it starts here. Instead of starting at 0, 0, it starts at 0, 2. But the behavior of the parent function is still maintained. Up 1 over 1, up 2, over 1, up 1, over 4, up 2, or up 2 over 4, however you want to think about that. So it looks like this. We're going from x equals 0 to x equals 4. And y equals 0 is the x-axis. So this is our region that we're going to be rotating about the x-axis. So it goes around like such. And so it looks like this. Looks kind of like a gumdrop or something, right? Kind of looks like kind of a gumdrop. But once again, our cross sections are just going to be circles, and each circle is going to be defined by this radius here. Okay, which is defined by the function. Okay, so define the volume of this figure. So again, A to B, area of the disk, dx, integrating with respect to x. The area of each one of these disks is pi r squared. So we're going from 0 to 4, in this case, pi, and our radius is going to be defined by this function, which is root x plus 2 squared. Okay? So, now what we're going to do is I'm going to take this pi out, because it's just a number, from 0 to 4. Now what I have here is a binomial, so I can't just square each of the terms. I have to FOIL it. Root x plus 2 times root x plus 2, that's what that squared means. So once I FOIL this out, root x times root x, can use FOIL, root x times root x is just simply x. Root x times 2 is 2 root x. Root x times 2 is 2 root x. And then 2 plus 2, or 2 times 2 is 4. Okay. And I can simplify this. I just get x plus 4 root x plus 4 dx. Alrighty. Now, I want to rewrite root x as a rational exponent. It makes it more easier for my calculus calculations, the mechanics involved. So this is what I'm going to be taking the antiderivative of. Okay? All right. So since I run out of space, I'm going to go ahead and clear this out. You can rewind if you need to go back and look at that a little bit more. Okay, so going from 0 to pi, 0 to 4, x plus 4, x to the 1/2 plus 4 dx. Now I'm going to take the antiderivative of all this. The antiderivative of x is 1/2 x squared. Now I'm going to add 1 to 1/2. 1 is the same as 2 halves. So I have x to the 3 halves. My new exponent goes to the denominator. My coefficient goes to the numerator. Plus 4x from 0 to 4. Okay. And I'm going to simplify this a little bit. 4 over 3 halves is simply 4 times the reciprocal of 3 halves, so it's 4 times 2 over 3, which is 4 times 2 over 3, which is 8/3. Plus 4x from 0 to 4. Okay, so now we're going to plug in our limits of integration in for x. And so I got 1/2 4 squared, plug in top one first, plus 8/3 4 to the 3/2, plus 4 times 4. And what's always nice is when you have zeros, one of your limits of integration, when you take the antiderivative of any expression, there's going to be the variable x in all of them, so when you plug in 0, that just becomes 0, so that's just going to be 0. Oh, happy day. Okay, so first off, this first one's easy. 1/2 times 4 squared is 16. 8/3 times 4 to the 3/2. Now, remember, 4 to the 3/2 is the same thing as saying 4 to the 1/2 cubed. You take the root denominator first and raise it to the exponential numerator. So 4 to the 1/2 is simply saying 4 square root of 4, which is 2, cubed, so 4 to the 3/2 is 8. Plus 16, and there we go. So we have pi. 1/2 of 16 is 8, plus 64 over 3, plus 16, which is 8 is 24 over 3, plus 64 over 3, plus 48 over 3, which is going to be, so it's going to be 72, so 136 over 3, so 136 pi over 3 units cubed. Alrighty, not too bad, all right? All right, let's look at one last one. All right, here we go. All right, so now this one is going to be a little bit different because we're not going from 0 to whatever our B value is, but no big deal. Okay, so it's defined by y equals x plus 1, which is a linear function, the parent function y equals x, translated up 1 unit. So you start here with a y-intercept of 1, you have a slope of 1, so up 1 over 1, up 1 over 1, up 1 over 1, so on and so forth. Okay. So this, we're going from x equals 1, which is vertical line over here, to x equals 2, and then y equals 0, which is the x-axis. So we're taking this region and rotating it about the x-axis. So it looks like this. Okay, it looks like a Rolo, right? Looks like a Rolo. Okay, and once again, our cross sections are going to be circles, an infinite number of discs. We're going to add them all up, the volume of all of them, and that will give us the volume for this Rolo that we're looking at. So once again, going from A to B, area of the disk, and area of a disk, simply pi r squared. Just remember finding the volume of them, but the volume is infinitely thin, so we just have to worry about the area. And now in this case, we're going from 1 to 2, not from 0 to something, but from 1 to 2. And pi we can put outside here, and our radius is defined by the function x plus 1, so it's x plus 1 squared, which once again we have to FOIL out. And once we FOIL that out, you get x squared plus 2x plus 1. We're going from 1 to 2. And we take the antiderivative of those values. You get 1/3 x cubed plus x squared 2 over 2 plus x from 1 to 2, which simplifies out to be 1/3 x cubed plus x squared plus x. So now it's just a little bit more complicated, but not really. Plug in 2 third 2 cubed plus 2 squared plus 2 minus, plug in 1 now. 1/3 1 cubed plus 1 squared plus 1. And you get pi. So it's going to be 8/3 plus 4 plus 2, which is 6, minus 1/3 plus 1 plus 1 plus 2, which is going to be 8/3 plus 18/3, because that's what 6 is, minus 1/3. Let's go ahead and just distribute this here. And 2 is going to be the same as, oops. Remember that negative is going to, what's this doing? Pin nutball on me. That negative is going to distribute that to 2, and that's just going to be 2 is the same as 6/3. So you get 26/3 minus 7 would be 19 pi over 3. Alrighty. Later, y'all.